Okay, I'm going to do a shear flow example, and we're going to do the same problem for two different shapes. So I pulled this figure 9.29a out and just changed all the dimensions so that they match. So these two boxes are built different ways, and we're going to compare what can carry the biggest shear force. So we have a wooden box beam. Is fabricated from 4 boards. So we actually have 2 different wooden box beams. And the first one is shown in figure 9.28, and the second one is shown in figure 9.29. The nails for both boxes are installed at a spacing of 125 millimeters, so that would be on center. So the nails are placed every 125 millimeters along the box, and each nail can provide a resistance of a shear force of the fastener equal to 500 newtons. In service, the box beam will be installed so that the bending occurs about the z-axis. We are to determine the maximum shear force that can be supported by the box beam based on the shear capacity of the nailed connections. And then we're going to do the same thing for the second box beam and compare them. So we have our ultimate shear force equation is V equals shear flow times the moment of inertia over Q. And we know that Q, the shear flow, times the spacing is less than or equal to the number of fasteners times the shear force of the fasteners. Okay, so we need to find I and Q, and then we'll find little q, and then we'll be golden. So I will be the same for both, and how I'm going to do this is I'm going to find I of this whole outside box, and then I'm going to subtract I of this inside box. Okay, so that's our plan. So we have I equals the base of the outside box is 200 millimeters. The height of the outside box is 300 millimeters, and that's cubed. And that's all over 12. Now I'm going to subtract the inside box. The base of that is 120 millimeters. The height of that is 250 millimeters. That's cubed all over 12. And we get I equals 293,750, or 293,750,000 millimeters to the fourth. Because this is a rectangle, our neutral axis is in the middle at a height of 150 millimeters from the bottom. Okay, so our next step is to calculate Q. In this problem, the Q area is this whole bottom section here. And our Y bar for Q goes to the middle of that section from the centroid. So this is our Y bar. So big Q, first moment of the area, equals y bar times the area. So that equals 150 minus 25 divided by 2. We're going halfway into that beam. So that's millimeters. Times the base of this is a full 200. We have the 40, the 120, and the 40 again. So times 200 millimeters, and the height is 25 millimeters. And we get Q equals 687,500 millimeters cubed. All right, now we are going to calculate the shear flow. So Q from this equation is less than or equal to the number of fasteners times the shear force that the fastener can carry all over the spacing of the fasteners. So in this situation, the number of fasteners is 2. We're going to look at, just one section of fasteners. So we're looking at, we have one fastener here and one fastener here. So the number of fasteners is 2 nails times 500 newtons per nail, the capacity of those nails, all over a spacing of 125 millimeters. So Q equals 8 newtons per millimeter. All right, so then moving on to calculate the shear force that this whole beam, now this is the shear force of the beam, V. There's Ada barking, sorry about that. We have V equals shear flow times the moment of inertia all over Q. That equals 8 newtons per millimeter times 293,750,000 millimeters to the fourth, all over 125 millimeters. And that equals V, shear force in the beam that's allowed is 3,418 newtons, or 3.42 kilonewtons. All right, so now we are going to compare that to this configuration. In this configuration, I is the same. All the givens are the same. Y bar in Q is the same, but the area for Q is different. So now we're going to be looking at this area. So we need to calculate a new Q, but everything else, so we need a new first moment of the area, but our shear flow is the same. So the only thing that will change is our big Q and our shear force allowable. So our new big Q, Q2, equals, the Y bar stays the same, 150 minus 25 over 2. The area changes in only one dimension. The width is now this 120 millimeters. So it's 120 millimeters. The height of that area stays the same at 25 millimeters, and we get a Q2 of 412,500 millimeters cubed. Now we can plug that into the allowable shear force equation, and that's shear flow times the moment of inertia around Z all over big Q2. So this is V2. And we have 8 newtons per millimeter times 293,750,000 millimeters to the fourth all over our new Q of 412,500 millimeters cubed. And now our new V is 5,697 newtons, which equals 5.7 kilonewtons. Pretty awesome. So Q goes down. V went up. All right.